Good afternoon, everybody. Welcome to the MTL Seminar Series. And today it's our pleasure to have Professor Tsu-Jae from Berkeley. I happen to know her because of her groundbreaking work in MEMS, but today she's not going to talk about that. She's going to talk about CMOS, and I also understand from talking to Vicky that you know all the insides out of clean rooms. She's very handy.
So. Yes.
Well, without further delay, I would like you to take the stage and,
Sure.
and start. Thank you for coming.
My pleasure. Thank you very much, Luis, and thank you all for coming. I know it's approaching final exam period, so that people are busy and distracted with other things. Thank you. Okay, so the title of my talk today is, well, what I'd like to talk about today is how we can extend the era of Moore's Law. So it's nothing, I know a lot of the research done here is on beyond Moore's Law, but I thought, it'd be good to see that there's still quite some time for Moore's Law, before the end of Moore's Law. So that gives you more time to develop, things beyond Moore's Law. So just to review, because I'm going to come back and talk about the fundamental, what has driven the growth of the semiconductor industry, and it's really economics. So in Moore's original paper, published in 1965, this is one of the plots. It shows the relative cost per component, and a component, nowadays we think of it as a transistor. Manufacturing cost per component in an integrated circuit as a function of the number of components per integrated circuit. And these are both on logarithmic scales, so orders of magnitude improvement as you go to the right, and improvement in cost as you go down. So what are shown here are curves representing the manufacturing capabilities at different points in time. So bottom line is that if you can integrate more components on an integrated circuit substrate, the cost actually goes down per transistor. But if you try to fit too many transistors on a substrate, in other words, fabricate them to be too small or packed too tightly, the manufacturing yield starts to degrade, and so then that causes the cost to eventually come up. So there's always some minimum cost point for any generation of manufacturing technology, and over time, that minimum cost point has moved to higher levels of integration. So fundamentally, Moore's Law is an economics law to lower the cost per component. The benefit of Moore's Law is to not only lower cost per function, but also on a single chip, you can have more components, so you can have greater functionality. So primarily, the industry has steadily been able to shrink down the size of the transistor to fit more of them on a chip at high manufacturing yield. And so this lowers the cost, but also we've had the benefit of improving system performance as well as transistor performance as it gets smaller. And so over time, this has enabled companies to develop better products that are more capable. The industry makes money and invests some of that back to further advancing the technology to further increase manufacturing yield for smaller and smaller devices. So this virtuous cycle has gone on for more than 5 decades and is still proceeding. And people expect it to extend for at least another decade in terms of seeing improvements in performance and functionality of chips. So what I'd like to talk about today is what I see as the pathway for continued transistor scaling to sustain that virtuous cycle. But also, fundamentally, it's really not about the transistor, the scalability of the transistor anymore that is causing Moore's Law to slow down. It's something else. So that's what I'd like to focus the second part of my talk on. Okay, so if we could take a trip back along the last, since the year 2000 or so, we can see how the CMOS complementary metal oxide semiconductor technology that's predominant in digital computing today, how it's evolved over time. Shown here is a sequence of cross-sectional scanning transmission electron micrographs of transistors at various generations of technology. So 90 nanometer node down to 32 nanometer node. And what we see here, it's kind of hard. I apologize for the contrast, but we have a gate electrode, and that controls current flowing in the semiconductor between the source and drain regions. And insulating the gate electrode from the semiconductor is a very thin layer of oxide. So this is why we have the metal oxide semiconductor transistor structure. What's interesting to see here is that these images are shown on the same scale. So you can see that the size or the gate length, the separation between the source and drain regions, which corresponds to the length or the width of this gate electrode, hadn't really shrunk over many generations. So what has happened, although the transistor density went up, that just meant that the transistors were packed more tightly, but the heart of the transistor was not scaled down. And I'll explain one of the reasons for this. But bottom line is the industry still made progress by introducing new materials into the manufacturing process. So if you look at the current flowing between the source and drain in a transistor when it's turned on, it's proportional to the width of the transistor channel. It's also proportional to the velocity at which the carriers are drifting from the source to the drain. So that's proportional to the effective mobility of the carriers, electrons or holes. And also the current in a transistor is proportional to the amount of inversion layer charge that forms a channel between the source and drain. And that is going to be dependent on not only on the applied voltage to the gate relative to the source above the threshold, but it's also proportional to the capacitive coupling or the capacitance between the gate and the channel. So what the industry did was they introduced new materials, let's say to introduce mechanical strain in the channel to boost the mobility. That enhanced performance. And then starting in the 45 nanometer generation of technology, they introduced advanced gate and gate dielectric materials to improve the capacitive coupling between the gate and the channel to boost the inversion layer charge density for a given operating voltage. And so we've been able to improve the transistor current per unit width to get faster and faster circuits, and at the same time fit more transistors on a chip because they made the source and drain regions smaller rather than the heart of the transistor smaller. Now, one of the reasons why it was difficult to scale down the gate length to miniaturize the transistor is because of fundamental limits in lithography. In other words, the process used to pattern those gate electrodes. So shown here is a graphic that illustrates features that the circuit designer would like to achieve, sorry about that, on a die. Right, so let's say it's an L shape like this. This is what the circuit designer would like to design, let's say the active region or the silicon or the gate electrode to be shaped as. So you have a photolithographic mask through which light is shined onto the wafer to develop the same image in the light-sensitive material, photoresist on the surface of the wafer. So then you can transfer the pattern from the mask to the wafer, to the integrated circuit layer, like the gate electrode. Now, this was pretty straightforward when the feature size was larger than the wavelength of light used in the photolithographic process. But as you go down to sub-lithographic features, sub-wavelength features, the mask had to be more complicated with extra serifs and so on in order to print any feature similar on the wafer, similar to what the designer wanted in the first place. So we have things like optical proximity correction, features on the mask, phase shift masks, and changes in the illumination system to try to achieve features on the wafer with good fidelity to what the designer wanted. But bottom line is, as the features got smaller than the wavelength of light, these features started to have curvy shapes, right? So if you want a rectilinear feature, you actually on the wafer did not achieve that. So let's see the impact of this sublithographic patterning issue over in real products. So here are plan view scanning electron micrographs of a static memory cell. So static memory cell comprises 6 transistors. There are 2 inverters, so there's pull up and pull down, PMOS and NMOS transistors. 2 inverters, so there's pull up, pull down transistors, 2 sets, they're cross coupled. And then to access the storage, the information stored, we have pass gate or access transistors here. So wherever the gate electrode passes over silicon, you have a transistor. Okay, so this is the original typical layout for 6 transistor SRAM cell. But starting at the 65 nanometer generation of technology, Intel went to actually a larger cell size. So if you look at the size of this rectangle, which delineates the SRAM cell with 6 transistors, is bigger than this rectangle because we're trying to sort of show them proportionately. So the industry went to a larger layout in order to be able to facilitate straighter features that were easier to print with good fidelity. So if they could print these with better fidelity, then they can make them smaller. And then this way, even though this size is larger, like 150 f squared, which is where f is the minimum feature size, you can actually go down to smaller f. And so so now you have a slightly different layout. You still have 2 inverters, and pass gate transistors like this. And this made it easier to scale. The next generation of technology, you see even better defined rectilinear features, and that's because they used multiple masks now to pattern the gate electrodes here versus one mask, one lithographic mask to pattern that. Now the reason why we had to do something like that, go to more process steps to pattern one layer of this integrated circuit, is because the transistor is sensitive, the transistor performance, the threshold voltage in particular, is sensitive to the width of the gate length and the channel width. So let me just explain that in a little more detail here. So we show the cartoon layout. Green is the silicon, and red represents the gate electrodes. So that's the ideal layout that the circuit designer would like for an SRAM cell. But with sublithographic features, you get rounded features like this. So what's worse is that you pattern the active area, the green patterns on the silicon, and then you align the mask for the gate to pattern the gate electrodes to the existing features, the green features on the wafer. And there's always going to be some misalignment, right? You're never going to get 100% alignment, perfect alignment everywhere. So in this case, we have what I've shown is the gate mask is misaligned to the left just a little bit. And so what you see here is that for one side of the SRAM cell, the gate length is actually reduced, right? The separation between the source and drain regions is actually reduced here. But then on the other side of the cell, the average gate length is increased. So basically, by lithographic mask misalignment, you actually make the SRAM cell asymmetric this way. Okay, so you're making one inverter switch at a different voltage, and you're making the other inverter switch at a, let's say, lower voltage on this side, but higher voltage on the other side. So it's imbalanced. That's what happens when you misalign the gate mask to the left. But if you misalign the gate mask to vertically, you end up with changes in the effective channel width that are, again, opposite for each side of the SRAM cell. So the industry went to, well, let's get rid of that problem by let's pattern the gate with two masking steps. So the first mask defines straight lines like this, and second mask is used to cut the hard mask, let's say, to pattern the gate. So you use two lithographic exposure steps to define one IC layer. This way, you don't have any variation in the gate length, right? If you misalign the gate pattern left and right. Okay. Now, the reason why that was important is because if we look at the SRAM circuit, the way that the SRAM cell works, let's say we want to read the data out. You pre-charge both the bit lines high first, and that causes the inverter characteristic. One of these inverters is not going to come all the way down to 0, right? It's like this. And then the other inverter characteristic looks like this. So this is just voltage on one node versus the voltage on the other node, and only where the IV characteristic or the transfer characteristic for each inverter has to be satisfied. So the only stable points of operation are where those two curves intersect. So you can store a high voltage or low voltage in two stable states. And in any circuit, you have to allow for noise in the system. So the supply voltage can be noisy. So you want to be able to have these curves shift left and right or up and down and still not lose these stable points of operation. But what happens with an asymmetric change in the threshold voltage for one inverter versus another, you can shift one of the voltage transfer curves this way. The other curve would shift in the opposite sense. So you can see that this margin here, by which you can shift left to left and right or shift up and down, the noise margin is degraded. So if you want to have high yield, like for megabit SRAM arrays on a chip, you can't really lower the voltage too much if you have to deal with this kind of variability. So this process-induced variation. So this basically either affects your cell manufacturing yield or just prevents the ability to lower the voltage. So this is true only because the threshold voltage of a transistor, the planar bulk MOSFET, was quite sensitive to variations in the gate length and in the channel width. So one of the reasons then, one of the benefits of going to an advanced transistor structure like the FinFET is that by having the gate straddle the channel region rather than just lying on the top surface, you can actually have better control of the channel potential by the gate. So if you look at this is only true if the width of that fin is narrower than the gate length. Okay, so if you design a FinFET properly, the current versus gate voltage characteristic will be steeper. Right? This just shows better gate control, better control of the current with the gate voltage. And that reduces the short channel effect. But also it has the benefit of giving you better on-off current ratio, which either provides better performance or allows you to lower the supply voltage and still get good performance. So one of the benefits of FinFET technology is that you can have low power products with good performance and high yield, and low cost. So back in the early 2000s, we showed that the FinFET could be scaled to below 10 nanometers in gate length. Intel announced that it was going to put it in production in 2011. It did so in early 2012. The one key thing here is that the current of the FinFET flows primarily along the sidewalls. And so the taller you make the fin, the more current your transistor will conduct. And so of course, circuit designers would like to have some wide channel devices as well as narrow channel devices in different parts of the circuit. And so that would mean taller fins somewhere and shorter fins elsewhere, but that's not really easily manufacturable. So the industry went to using multiple fins in parallel to increase the drive strength of a FinFET transistor. So that's how it's done. Now back then, the smallest feature on a chip was the gate length. So how did we make a fin? How do we define a fin with smaller features in the gate length? We did this by using a process called spacer lithography. And some companies in Japan called it sidewall image transfer. Today, the industry calls it self-aligned double patterning. But basically, to pattern the fins of a FinFET, and we started with a silicon on insulator substrate, is we use ordinary lithography to define, let's say, a stripe. This is a cross-section of a stripe. And the stripe we initially used silicon germanium. And I'll explain why later. Then we can deposit conformally by conventional chemical vapor deposition an oxide or nitride layer. And because it's conformal, vertically it has a greater thickness along the sidewalls here. And if we etch back this deposited layer anisotropically, we can end up with these sidewalls along the sidewalls of this lithographically patterned feature. Now, the width of these spacers is really dictated by the thickness of this thin film deposition, and that could be easily smaller than the wavelength of light used in the lithographic process. Then we can selectively remove this sacrificial material, which today the industry calls a mandrel material, and then use the spacers to pattern the fins. So this is what we did to form the first FinFETs with very short channel lengths. And notice we have two fins or two features for one feature that was defined lithographically. So this is one reason why the industry refers to this technique as double patterning, because you get double the density of features than you started out with originally. Okay, if you look at the roadmap or the past scaling of the FinFET, it's scaled steadily every 2 or 3 years. A new generation of technology has been put into production. But the main thing I wanted to point out here is from Intel's 22 nanometer generation FinFET to today's 10 nanometer generation FinFET, which is in some production now this quarter. You can see that the fins are getting narrower and taller. So the industry is developing the techniques to manufacture with high yield, tall and narrow structures with tight pitch. Okay, so this means that you can go to fewer fins to achieve a large transistor drive strength. This is how you can also save area. So this is what has resulted in maybe scaling of area even faster than Moore's law would have dictated. But I wanted to come back to the SRAM cell. It turns out that for the SRAM cell, if it's more ideal to have the pull-down, the passgate transistor to be stronger than the pull-up transistor. Now for a FinFET, the sidewalls, the crystalline orientation of the sidewalls is not 100, it's 110 plane. And so that actually provides for higher hole mobility, but worse electron mobility. And for that reason, the strength of a P-channel FinFET is similar, very close to the strength of an N-channel FinFET for the same fin dimensions. And so this is actually a problem for an SRAM cell. And so if you want to have an SRAM cell operate at low voltage with high read and write margins, you actually have to have two fins for the passgate device. And you might as well do that for the pull-down device as well, because it's not going to change the area. So you need two fins to make the N-channel devices stronger for a single fin for the P-channel pull-up devices. But this takes up more area. Ideally, you'd like to have a more compact area because at least half of the transistors on a chip nowadays are used for SRAM, for memory, for cache memory. But the issue here is that there's poor writability. It's not easy to write information into that SRAM cell. So let me explain why. So let me just explain how you read and write information into an SRAM cell. You have two inverters here storing high and low voltage in either of the storage nodes. And you access the information through these pass gate devices. So when you read, as I mentioned before, you pre-charge the bit lines high. And the side of the cell that has low voltage stored, that cell, so basically what we want is this bit line to be pulled low when you read the information. That means that this N-channel device has to pull down this bit line to a low voltage through this pass gate transistor. Now, when these devices are on, it's sort of forming like a voltage divider. You just want to make sure that the voltage here is low, so it's not going to be high enough to trigger this inverter to flip. So this turns out to be not an issue to achieve because the source voltage of this pass gate transistor is higher than the source voltage of this pull-down transistor. So naturally, this pull-down transistor will always be stronger than this pass gate transistor. So there's no problem to read information in a 6T SRAM cell if the size of the pass gate transistor and pull-down transistors are the same. Now for write, it's a little bit different. Let's say we store, we have the same information stored, but now we'd like to change the information in the cell, flip this storage node from high to low. So we put a low voltage on this bit line, and when we activate the pass gate transistors, we turn on the pass gate transistors. We want the pass gate transistor to pull down this storage node low. Now it has to fight this pull-up transistor, whose job is to keep that node high. So here, you need the pull-up transistor to be weaker, than the pass gate transistor to successfully write into this cell. Now, as I mentioned before, because the P-channel FinFET is almost as strong as the N-channel FinFET, it turns out that if you have the same size pass gate and pull-up devices, that the writability current, is rather low. Okay. So fundamentally, then, how do we continue Moore's law, scale the size down, right, to fit more transistors or more cells on a chip, have more functionality for a chip, and get around this problem? Now, with a FinFET, you really can't change the channel width, the effective width, very easily. You can change the number of fins. So what my group has published in the last couple of years, and now there seems to be interest among companies to try this out, is what we call inserted oxide FinFET, or iFinFET. Now, here's conventional FinFET, okay? So at the 5 nanometer node, the roadmap sort of predicts that it'll be like, 40 or 50 nanometers tall, but the fin width will be 6 nanometers wide. Now, the iFinFET has an inserted layer of oxide, like, let's say, roughly halfway through. We originally came up with this idea because what we do by inserting an oxide layer there, we allow the gate fringing electric fields to penetrate the channel region, and that the extra fringing electric fields helps to improve gate control. So it turns out that the iFinFET is more scalable than the FinFET, and we've published that in a separate work, which I won't really show here. But the idea here is that we have inserted oxide layer.
How do you insert the oxide?
So I'm going to show that in a slide. But the nice thing here is that you can actually, that oxide layer can act as a diffusion barrier, dopant diffusion barrier. So you can actually implant and anneal and fairly uniformly dope that upper, I'll call it nanowire channel. So essentially, you're weakening this FinFET, this iFinFET, because now the effective channel width is just down here, right? So in this work, and this is simulation work that I'm going to show. Basically, we just dope this heavily, but not so heavily that gate-induced drain leakage becomes a problem. We just dope it to just make sure that this upper part of the FinFET doesn't ever turn on. Now, you can't do that with the FinFET because if you implant up here, first of all, you can't really precisely control the effective channel width by implantation. And other people have published, well, we can actually have different heights of fins by recessing the STI oxide, different amounts. But if you want to do this in small areas, and it's not as easy or not as straightforward from a process integration standpoint. So to answer Hank's question, the iFinFET, how is a FinFET fabricated today? You start with a bulk silicon wafer, you pattern tall and narrow fins, you form and recess shallow trench isolation around those fins, right, to expose the skinny part. So you allow a gate electrode to wrap, a gate dielectric and gate electrode to wrap around it. That's a dummy stack. Form the source and drain, you etch away the source and drain regions and regrow them to form the stressors, right, the source drain stressors to enhance mobility in the channel. Then you remove the this dummy gate stack and deposit your high K, a metal gate stack and so on. So this is a conventional FinFET process. The iFinFET uses the exact same process, except you start with an SOI substrate. So the industry has the access now to SOI substrates with very thin buried oxide layer, ultra thin box, like 5 nanometers. So basically, since you're etching away the source drain regions and regrowing them, the source and drain regions don't have that oxide in them. They're continuous, silicon germanium or silicon doped with carbon and so on. So the source and drain regions don't have that inserted oxide layer. Only the channel region has that inserted oxide layer to enhance gate control and also to allow for fine tuning of the strength. So depending on how thick that SOI layer is to begin with, if it's thin or if it's thicker, you can actually adjust the position of the inserted oxide layer. Of course, this is for all the wafers on your chip. So you can insert it, if the SOI layer you start out with is pretty thin, then when you kill the top nanowire portion, it's not going to really degrade the drive current too much. But the thicker the SOI layer is, the more the weaker the effective channel width. The effective channel width is tuned by changing the position of that inserted oxide layer. So you can very precisely control the drive strength with FinFET by just starting with an SOI ultra thin box SOI wafer. And as I alluded to before, if you look at the drive current of a undoped iFinFET, it's better than that of a FinFET because you have better gate control. Okay, and the regular undoped iFinFET, the performance is not really sensitive to the position of that inserted oxide layer. So we've done some simulations. We've developed a technique to predict SRAM yield and so on. But the key here is that if you have higher operating margins, then you should be able to more aggressively scale down the operating voltage. So the minimum operating voltage of a 6T SRAM cell, we looked at the impact of the position of the inserted oxide layer on the minimum voltage needed to guarantee 6 sigma yield for writability and 6 sigma yield for readability. So you can see that the poor writability of the FinFET-based SRAM cell means that you can't really lower the supply voltage for an SRAM cell. You can if you implement write assist circuitry. So if you boost the word line voltage during write, or you purposely lower the voltage of the inverters during the write process, using these circuit techniques, you could operate a minimally sized 6T SRAM cell at lower voltage. But this write assist circuitry requires overhead, an area, and operation of the SRAM cell. Now, if you use the iFinFET and you only dope the pull-up, the P-channel devices to weaken them to improve writability, depending on the oxide position, as you weaken the PMOS devices, you can actually lower you improve the margin, so you can lower the voltage needed, the minimum operating voltage for assuring 6 sigma write yield. So the key here is that the nominal operating voltage for 5 nanometer generation CMOS technology is 0.65 volts. And this minimum operating voltage for the SRAM cell is below that. So in other words, you eliminate the need for write assist circuitry by using the iFinFET technology. Okay? And the reason why it worsens later is because as you lower the effective channel width, random dopant diffusion, the random dopant fluctuation variability starts to increase, so then the yield gets worse. Okay, so I've just shown you the pathway, I think, to continue to scale CMOS. And we know that ultimately there is a fundamental limit, and that's really dictated by quantum mechanics, right? Even if your transistor, the gate, can control the channel potential to make sure that there's a high potential barrier in the off state, if the source and drain are too close together, it's hard to prevent direct tunneling, so it becomes difficult to turn off the transistors. You lower the gate voltage, you really can't turn it off properly if the channel length is very, very short. However, if you have some advanced channel materials, like I know some of you are working on today, that have higher tunneling effective mass, it is possible to get to smaller channel lengths. So, recently people have demonstrated that you can have a gate, let's say a 1 nanometer diameter carbon nanotube, just for demonstration purposes, that it is possible to get transistor good transistor switching behavior, turning on and off, even with a gate length of 1 nanometer, if you have a channel material that has lower tunneling effective mass. So bottom line is that there's plenty of room for continued miniaturization of CMOS devices to sustain Moore's law. And another issue is that if the operating voltage cannot be aggressively reduced, then the power density is going to go up as you pack more transistors together. And there's, of course, good work being done on tunneled transistors, negative capacitance transistors, to really steepen further the subthreshold swing so we can further lower the operating voltage. And once you lower the operating voltage below the threshold voltage, you don't get any benefits. So if we can, with steeper switching devices, lower the operating voltage further, we can reduce the energy per operation for a given level of performance to overcome the power density challenge for CMOS. Okay, so there's plenty of room for a further scaling of CMOS. So that's not what's going to limit or threaten the end of the Moore's law. What I think is going to be a problem is lithography, right? The cost, right? Moore's law is all about economics. So today, let's revisit the self-aligned double patterning. I showed how you can use the self-aligned double patterning technique to pattern like 2 features for 1 lithographically defined feature. I just want to show here you can also use this technique to define 2 trenches, right? With with this approach. So let's say we use lithography, normal lithography, to pattern the mandrel, the sacrificial material, deposit the spacers and make the spacer layer and do anisotropic etch to form the spacers. Then you can use a second mask like this to form this, the photoresist features here. This is shown in plan view here. So this is a second mask. So first mask was used to pattern these mandrels. Second mask used to pattern the regions where you want trenches. And then you can actually end up with trenches, and then with the metal layers you can deposit, copper and polish it back to form 2 copper lines, for example, if you want, at higher density. Right? So self-aligned double patterning, spatial lithography is used today to form straight features with sublithographic minimum dimensions and sublithographic pitch. And if you look at, this is just taken from a talk that was presented by Intel, just to show you the range of pitches. So if you use 193 nanometer lithography, you can get down to, let's say, 80 nanometer minimum pitch. If you want to go smaller than that, you have to use self-aligned double patterning. And if you want to go smaller than 40 nanometer pitch, you have to do double patterning, the spatial lithography, twice. So you have to do spacers on the sidewalls of spacers to get this higher density. But if you notice, there are many steps, right? Deposition and etch and so on in a double patterning process. So the issue here is that in the past, for every single layer in the integrated circuit, and there are many layers, you just use 1 photolithographic exposure step, 1 mask, to pattern it. But now, in the future, the number of masks needed to pattern each layer is growing quite rapidly. So today, it's not uncommon to use 5 masks to pattern 1 critical layer in an IC. And when I've talked to people in the industry, they actually are anticipating in the future, the most dense layers, let's say in the metal, will take over a dozen masks. They will use over a dozen masks to pattern 1 layer. So you can imagine that this is not Moore's law, right? Moore's law is all about roughly the same number of process steps, but double the number of transistors as you advance the technology. If you need to double the number of steps to double the number of transistors, that's not following Moore's law. So this became apparent a few years ago. This is just a quote from the industry newspaper in 2014. So at that time, I thought, well, okay, if this is what's going to slow down Moore's law, we've already done all we can to show that there's plenty of room left for scaling the transistor. Why don't we just help the industry come up with a lower cost way of patterning sublithographic features at sublithographic pitch? So the idea is very simple. Ion implantation today is actually one of the most inexpensive steps. It's almost as cheap as a wet clean, and it's very uniform across large areas. So it's well controlled, and implantation can be done precisely at different angles. So let's say we have a hard masking layer on the surface of your IC layer that you'd like to pattern. So in this case, it's just a thin layer of silicon dioxide. So we can implant it to cause damage in that layer. But if there are pre-existing features, let's say photolithographically defined, on the surface of that hard mask, well, then you have the shadowing effect. So the damaged region can be arbitrarily small, right? It's just a matter of adjusting the tilt angle or the height of the predefined features or the width of that trench. So it's pretty simple, right? So experimentally, if you look at the etch rate of silicon dioxide, and this silicon dioxide is only 5 nanometers thick, if we look at the etch rate as a function of depth, if it's not implanted, it's really low because this is a very dilute solution of HF. So this is a typical solution you'd use just to clean the wafer before putting it into a furnace or gate dielectric formation process. But if you implant a moderate dose, so 2E14 is certainly much less than what people would use to, let's say, dope the source drain regions. It might be used to dope the channel and so on. So a very modest dose of argon at low energy, right? So it's just contained within the silicon dioxide layer. The etch rate actually can be enhanced by 6 or close to 10 times depending on the dose because you're damaging the oxide to make it easier to etch away. And we look at the etch rate as a function of the depth and correlated that with the simulated implant damage profile, and it correlates pretty well. So this confirms that the mechanism here is just breaking bonds with the argon implant to make the oxide easier to etch away. So how do we apply this to double patterning? Well, let's say we have some spacers defined on the surface of the wafer. In this case, experiments that we did, we used silicon as a spacer material. So we have linear features on the surface of the wafer, so it's a cross-sectional view. Have a silicon dioxide hard mask. We can do a tilted implant step like this to damage the sublithographically defined linear regions here, and do a second tilted implant at negative tilt angle. Okay, and then you can dip it in dilute HF. You end up with twice as many trenches as you started out with originally. And the size of those features can be arbitrarily small. Now, the first proof of concept, we just did a single tilt. And this is actually nothing new. People in the memory chip manufacturing business have done this to get sublithographic features. Basically, we did a 15-degree tilt implant. And these are the pre-existing features on the surface, implanted into a thin layer of oxide. Now, it's really hard to see the thin layer of oxide in a cross-sectional SEM. So what we did was, after doing the HF dip, we did a silicon etch, which is highly selective. It doesn't etch if there's oxide on the surface, it doesn't etch the silicon. But if this oxide is gone, then it'll etch the silicon. So you can see that the silicon trench widths are certainly narrower than what we started out with the hard mask. And it does correlate well with the features size we expect based on the tilt angle and the original height of the pre-existing features. Now, if you look top down, what do those linear features or the trench look like? What does it look like? So this dark band here this is a plan view SEM. Here we have the hard mask, the amorphous silicon was kind of wide. Okay, so these are the hard masks. The edge, naturally, because of the photolithographic process, the photoresist does have some line edge roughness. Okay, and then that line edge roughness is sort of replicated in the edge of the implanted region. So this is the non-implanted oxide here that remains. And in this region, the tilted angle damaged the oxide and it was removed and the silicon was etched. So if you look at the position of the edge of like this edge, you can see that it correlates pretty well with the edge, the position if we shift it, of the original hard mask. So it's a nice correlation there. But interestingly, line edge roughness is also a challenge for the industry today. If you have variations in the let's say if you have line edge roughness in a gate electrode feature, that leads to gate length variations, which affects the transistor performance. It leads to variation. So we'd like to have low line edge roughness, especially at the low spatial frequencies. At high spatial frequencies, it doesn't matter, right? So it turns out that the tilted ion implantation defined edge does show lower line edge roughness at the lower spatial frequencies. Okay, so sigma is, like in this case, 2.58 compared to the original line edge roughness of the hard mask, which is 2.73 nanometers. At higher spatial frequencies, because of the stochastic nature of the implant process, the line edge roughness is larger, but that doesn't affect the transistor performance. Now, the obvious question would be, what is the resolution limit of this implant lithography process? If we look at, from simulations, what my student did was simulate at different tilt angles there's going to be some lateral straggle of the implant, of the ions here, right? So that's going to lead to some line edge roughness. So that's what this plot shows, is like the latent line edge roughness of the, due to ion straggle in that oxide, how it depends on the tilt angle. So, the shallower the implant, obviously, then the larger the straggle. So as long as the tilt angle is less than, let's say, 30 degrees or so, it's well below a nanometer in line edge roughness, just due to the stochastic nature of the implant process. So looking closely then, you can see that the minimum trench size that we've actually achieved with our approach in the lab is less than 10 nanometers. And indeed, from simulations, we also determined that the minimum feature size is well below 10 nanometers for this approach. So just to show you, if we do two tilted implants, positive and negative angle, we have a single trench to begin with. We ended up with 2 trenches in the end. And the sidewall slope, of course, that depends on the etch selectivity of the process, the silicon etch process, and of course it can be improved upon, from what we have in the lab. So bottom line is, we believe that this technique can be used to achieve pitches below 20 nanometers. So you can use conventional spacer lithography, self-aligned double patterning, to get you part way, and then do this additionally to let's say increase the increase the density of your fins, right? If you're making fin FETs. And so yeah, plan view definitely shows this. So bottom line, the fundamental reason why we looked at this is because of cost. So let's compare, this is the self-aligned double patterning process that I went through before to, let's say, form the silicon fins, for example. With the tilted ion implantation approach, you don't need a mandrel layer. Instead of depositing and etching back a spacer layer, you just do positive and negative tilt angle, and then you just do the silicon etch, and you can remove the hard mask. So it can be a lot cheaper, let's just put it that way, than spacer lithography. And on top of that, the resolution limit is better. So I think that can really help. Now, it's not only limited to linear features. So the little poster, that image that I provided, we've experimented with nonlinear features as well. But just for example, if you want to make very, very small holes for whatever reason, a contact hole, you can start with lithographically defined like hole that's this big. But with tilted implantation, you can achieve certainly sub 20 nanometer, sub 10 nanometer holes. So this might be interesting for other applications that you have in mind. So what I'd like to do next, though, is really apply this technique to further reduce the cost more drastically. So today, the most advanced chips have over a dozen layers of metal, right? So the metal layers that have the tightest pitch, the metal lines are only running along one direction, and then the next layer, in the orthogonal direction. So if you want to connect a transistor from one part of the chip to another part, you need to go through multiple layers of metal, right, running horizontally and vertically across the chip. And the reason that the industry had to do that is because of these sublithographic patterning techniques. But with tilted ion implantation, it can actually enable 2D layouts again. You can have, in the old days, like I showed the SRAM cell, you have like L-shaped or zigzagged patterns on each layer of your IC. The reason why we don't do this today is because of this. You can't really print that with good fidelity. But we can do this with tilted ion implantation. So for example, the way you do this is you would still have a hard mask layer over your IC layer. Now you use multiple lithographic masks in sequence to damage the oxide, the hard mask, according to this pattern. So in this case, let's say you could partition this pattern across 4 masks. Okay, so the first mask would be and you do an implant to define this part of the pattern. To use a second mask to define this next section of the pattern, and so on, right? Now, you might say, well, there's a lot of masks, but as I mentioned today, they're already thinking of going to a dozen masks, right, to pattern one layer, and that's still with straight lines, right? So very restricted layout. Here, you don't have a restricted layout, and so you can actually now potentially reduce the number of interconnect layers needed to wire your chip. So only after you do all these implants, the damage is accumulated, but it doesn't matter, it's going to be etched away. Now you can actually, after doing all these implants, you can etch the hard mask layer to realize this pattern in the hard mask and then transfer it to the IC layer. So I think this is interesting work that can be done in the future. And so I'll just summarize here that, yes, this virtuous cycle will continue There's still plenty of room if we continue to advance transistor structures, and new materials can enable that. But I think we'll need more and more innovations in the process, the integrated process technology, to really lower the cost of manufacturing in order to extend the area of Moore's law. So bottom line is, this cycle will continue, but just different things will be driving it, not necessarily transistor scaling. And this work, I have to acknowledge, of course, the students and postdocs who did the actual work and sources of funding. So thank you very much for your attention. I'm happy to take questions.
Well, thank you. Now we're open for questions. Just wait until I hand over the microphone so we can hear and record the question.
Thank you very much. It's a very interesting talk. I just have a very simple question.
Yes.
Talking about the self-aligned TIA.
Yes, TII.
TII, double or multiple patterning.
Right.
Do we need automatic recognition of those patterns? If so, how could we do that?
Automatic recognition.
Of those patterns.
Oh, you mean automated generation?
Yes.
Oh, okay. So today, with self-aligned double patterning, okay. So today, multiple lithography, multiple masks are already used to define a single layer. So there already are programs to automatically partition, the pattern across multiple masks. So I think that should be relatively straightforward to do with this technique. In fact, spacer lithography is more complicated because the spacers, if you look plan view, they wrap around the ends of those mandrels. So you need an extra mask sometimes to cut them. So actually, if you think about it, with tilted ion implantation, there's no need, you can get away from the need to cut any, there's no, you can avoid the need to have an extra mask just to cut the ends of the doubly defined pattern features. I mean, if you think about it, yeah. So I think that issue should be only simpler with this approach to generate the masks needed. That's a good question.
Okay.
Yes.
Hi. Thank you for the great talk. I have also a simple question. When you are doing spacer lithography, you may have line edge roughness, but the line width roughness is very small because the edges are correlated.
Yes.
In this technique, the edges are not correlated. Isn't this going to be a problem?
That's an excellent point. So that's one reason I also said, if yeah, that's true. That's true. So the width of the spacers is relatively uniform, even though the spacers might not be smooth. So the line edge roughness is improved with this technique, but yeah, could be worse than for spacer lithography. But if you start with spacers as the pre-existing features on a mask, maybe that can be mitigated. Yeah. So I think last year, basically as companies are trying to make FinFETs with smaller layout area, they want tighter and tighter fin pitch. And with these spacers, if the spacers are too close, they start to, during the manufacturing process, start to like collapse on each other. So if you start with spacers that are really as small pitch as possible, then use tilted implantation to double the density of fins. I think that's an easy way to use this technique, because spacers, physically, they're just going to collapse on each other if you make them too close. So this can get you to, past, let me see. I think I showed this. Together with spacers, yeah. Right, so if you look at the international, there's a new roadmap. The industry is planning to go below 20 nanometer, minimum pitch, right? So you could use self-aligned double patterning and then use tilted ion implantation to get easily into that range or beyond. That's what I think would be most practical.
Wow, it's been a while. This is pretty amazing. When you do the implants with the argon, I couldn't quite tell. Are they ever coming into the fin? And if so, then is there any damage issues with this kind of implantation of this amount of argon? That's
a good question. So we purposely made the hard mask pretty thin, like 5 nanometers. And the implant, the nice thing about this dose is actually, even if some of this went into a little bit, part of it went into the silicon underneath, it's really easily annealed out because it's such a low dose. It's not even going to be amorphizing the silicon, even if it went there. So it is important. So we did this in collaboration with Excelis. So it's easy to implant at pretty low acceleration voltages. But we did find if we went to too low of a acceleration voltage to get shallower implants, there's the ions, they tend to spread, right? So yeah. So there's you don't want to go too low in the energy to avoid damage, because then the resolution of this technique will degrade. But it seems to be just fine. Yeah, the argon, I think you can easily anneal out any damage.
Okay.
I forgot to put a slide here, but we actually have, what we did here was a thermally grown oxide. Of course, for patterning metal layers, you don't want to have thermal oxide. So we actually have looked at spin-coated silicon, carbon, kind of oxygen compounds, and we can get similar effects. So you can spin-coat the hard mask and cure it, and then use it to pattern the layers, the dielectric layers, to form the metal lines. So that's where some materials development work is needed. Yes.
So I'm an economist working on Moore's Law, so I was very pleased to hear you coming back to that theme. I was wondering if you have tried to do any sort of more precise estimation of, you've made this argument about how this is going to change costs. Have you tried to estimate actually how that's going to change these?
So we did so the one thing I learned is companies don't like to share their actual real costs. So it took a long time, and we had multiple sources. And we actually published a little article in Silicon Semiconductor, I believe. But anyway, to come up with this 60% number, because people weren't willing to share really, even relative numbers, like how much it costs for a dry etch. Like we asked Lam Research, how costly is a dry etch process compared to a wet etch? And they're not really willing to share too precise numbers. So got numbers from Soitec, from Lam Research, from other companies to come up with this number. But as I mentioned, potentially if we can actually even reduce the number of layers needed to in your IC, that can save a lot of costs also. So it's hard to estimate, but I think overall it can be half, right? It really depends, because if we look at the roadmap from what I've seen for, let's say, continuing to scale FinFET technology, it really is increasing the number of layers and the number of masks per layer. So it is going to be over 100 masks to define, to make an IC, the most advanced IC in the future. So if we can reduce that, and also reduce the number of layers, then I think it'll make a big difference. Yeah.
How about 3D patterning? Have you ever considered 3D patterning?
Using implantation. Yes, I guess we could do that by simulations, because you can implant like the sidewalls of 3D structures. Is that what you're saying?
Yes.
Yeah, definitely. So the nice thing here is that you can simulate the effects of this implant process and etch. So the TCAD simulation tools are capable. So it would be great if more people were to explore other 3D patterning applications.
If you have 75 mask levels in an IC process, are they all exposed to the same kind of tool in version 193, or is
that's
there
a good point.
concept for using lower cost tools?
Well, the lower pitch tools, I guess you could use, not the immersion tools. But so that's a good question, because what I've heard, because I've given this presentation at the lithography conferences, so the EUV tools that are coming online, initially they'll be used to do the cut or the contact holes, because there are going to be defects on the mask, right, that you can't avoid. So it's best to have sparser patterns so you don't have the patterns landing on the defects. But one interesting thing of the EUV tools is that you can't, the exposure tools are not interchangeable. You can't. So it's just going to become even more expensive. But I think with this approach, it should be, so the idea here, if I didn't mention it clearly, is that each of those lithographic masks is subcritical in terms of feature size, right? It's just a normal 193 stepper. It can be used to define each of those patterns.
Okay. Well, let's thank the speaker once more.
Thanks very much.